Hello everyone, welcome back to AI Academy's Python for Data Science series. In our last session, we discussed about the world of data visualization with Seaborn, explored a variety of plots like scatter plots, box plots, and histograms to uncover the stories hidden within our data. We learned how to enhance these plots with advanced customization options, making our visualizations not only informative but also visually appealing. Today, we're shifting gears to tackle a common challenge in data science, which is dealing with missing values. Last time, we worked with datasets that were pre-cleaned to ensure our visualizations are accurate. We intentionally ignored the missing data to keep our focus on visualization techniques. However, that's often not the case in real-world scenarios, where missing data is a frequent and is a critical issue that needs addressing. In today's lecture, we're going to dive into strategies for handling these missing values. We'll start by identifying where data might be missing and explore various approaches to filling in these gaps. Understanding how to effectively manage missing data is crucial because it can significantly influence the conclusions you draw from your analysis. So, get ready to add another essential skill to your data science toolkit. Let's dive in and learn how to ensure our datasets are as robust and reliable as possible, paving the way for accurate and insightful analyses. And don't forget to check out our previous sessions if you need a refresher on any of the visualization techniques we've covered. Alright, let's get our hands dirty with some real data handling in Python. To ensure that we can work with our data files efficiently in our analysis, the first step is to set up our environment. When importing it into we can make the first column our index column. This organizes our data neatly, making it easier to manage. We'll also specify some string values to be recognized as Python nan, not a number, to handle missing values right from the get-go. It's important to preserve the integrity of our original data and avoid accidental modifications, so we will create a copy of the original dataset. This way, any changes we make will be on the duplicate data, leaving our original data unchanged. So, from now onwards we will be working on the data frame df3. Now, with our data loaded and safely copied, we can proceed to manipulate and analyze this dataset without any worries about altering our source data. Let's dive into the next steps. Understanding how to identify missing values is a crucial first step in handling them effectively. In Pandas, missing values are usually represented by nan abbreviation of, not a number. This special value is used to denote missing or undefined values, typically arising from empty cells in your data files, such as CSVs. When Pandas encounter these empty cells during data import, it automatically converts them to nan. To systematically check for these missing values in your Pandas data frame, there are a couple of handy functions we can use like isnull and isna. Both functions are essentially the same and can be used interchangeably to detect missing values across your data frame. These commands will return a new data frame where each cell is either true or false. Cells with true indicate missing values, and those with false indicate non-missing values. This makes it easy to see at a glance where your data might be incomplete. So we see the syntax and output. The .isna method is applied to the data frame, which returns a new data frame of the same size, where each cell is a Boolean value indicating whether the original cell in data frame contains a missing value is true if the value is missing, otherwise false. And the .sum, this method is chained to the result of df3.isna. The sum method in Pandas, when used on a data frame of Boolean values, counts true values in each column. In the context of the data frame returned by isna, the sum method counts how many missing values are present in each column of the original data frame df3. So, in the output we can see that the age and fuel type column has 100 missing values, suggesting that data certain entries is not available. And the met color indicating if a car has metallic color shows the highest number of missing values at 150. The both isna and isnull gives the same output, and you can use any one of them. Let us now explore different strategies for dealing with these missing values once we've identified where they are. as having a clear understanding of where and how many missing values exist in each column of your data frame is vital for effective data management and analysis. So, let's move on to understanding of the extent and distribution of missing values in your data frame is crucial for forming an effective strategy to deal with them. As you've outlined, once we know where these missing values lie, the next steps involve deeper analysis to decide how best to address them. After identifying the number of missing values per column using either isna.sum or isnull.sum, we have made an essential observation, understanding whether the missing values in one column are related to missing values in another. This kind of analysis can reveal patterns in the missing data that may influence how you handle them. For example, if the same row's missing age are also missing fuel type, this could suggest a systematic issue in how data was collected or an entry error for specific samples. To investigate whether there are any overlapping missing values across columns, you can use a visual tool like Seaborn to plot a heat map of the missing values or use Pandas to create a more detailed report. Here's a simple way to check for multi-column missing value patterns. This will give you a count of missing values per row where more than one column has missing data. It helps in identifying if there are any rows that are particularly incomplete. So, we can see that there is no specific pattern in missing data across columns. Moving ahead, how to handle these missing values can generally fall into two broad strategies. The first one is, if a significant portion of a column or certain rows are missing values, and these values are not crucial for your analysis or predictions, you might consider dropping those rows or columns. This is often a straightforward approach but can lead to a reduction in dataset size, which might not be ideal. The second one is imputation, which is filling in missing values based on logical assumptions or statistical calculations. This could be as simple as replacing missing values with the mean, median, or mode of a column, or more complex imputations using algorithms that predict missing values based on other available data. The choice between removing data or imputing it often depends on the specific requirements of your analysis or the algorithms you plan to use, as well as the nature of the data itself. It's crucial to consider the impact of each choice on your results and to ensure that any imputations are made thoughtfully to avoid introducing bias. Indeed, the strategy for managing missing values largely depends on the pattern and extent of the absence in the dataset. In cases where a row contains almost all missing values, it often makes sense to remove that row entirely, as it offers little to no useful information and could twist your analysis if improperly imputed. To identify rows where at least one element is missing, you can use the isnull function along with the any method set over axis 1. This method checks across columns, axis equals 1, for each row, returning true if any column value is missing. Once you have isolated these rows, you can explore them further to understand how the missing values are distributed. For instance, checking the dimensions of this data frame will tell you how many rows are affected by missing value. In your case, you have found 325 rows with at least one missing value among the total columns. This information is crucial as it provides a scale of how significant the missing data issue might be in your dataset. After identifying where the missing values are, the next step is to decide on the appropriate handling method. You might also want to inspect specific cases where only certain variables, like age or kilometer, are missing. This can be done by filtering missing_data_frame to see if there are any common patterns or factors contributing to these missing values. Ultimately, the strategy should be dictated by the specific requirements of your dataset and the nature of the analysis you intend to perform. By examining the patterns and extent of missing data, as you have done, you can make informed decisions that enhance the reliability and accuracy of your results. When it comes to handling missing values in numerical data, the choice between using the mean or the median for imputation largely depends on the data's distribution. As you noted, the mean is sensitive to outliers and can be significantly skewed by them. On the other hand, the median, being the middle value of a data set when ordered, is more robust against outliers and might provide a more representative value for imputation in such cases. So let us move on to using descriptive statistics for imputation decision. The describe function in Pandas is incredibly useful for getting a quick overview of the statistics that summarize the central tendency, dispersion, and shape of a dataset's distribution. By examining these statistics, you can make an informed decision on whether to use the mean or median for filling missing values. From the output of the describe function, we can see that price variable detail like the mean value is 10,730, the median which is 50th percentile is 9,900 and the standard deviation is 3,626. And the range of the price is $4,350 to $32,500. Similarly for the age variable the mean age is 55 months and the median age is 60 months. The close proximity of the mean and median age suggests that this variable is fairly symmetrically distributed, so imputation with the mean might not introduce significant bias. Based on the describe output, for the age variable, where the mean and median are quite close, using the mean for imputation will be suitable. So, we impute missing values for age with the mean. The syntax for same is df3 age.fillNA, df3 age.mean, in place equals true. This code snippet will replace all nan values in the age column with the mean age calculated earlier, effectively smoothing over these gaps without distorting the overall data distribution. After that, once we verify the missing value again, we can see now that the age variable has the 0 missing value. So, by using the describe function to evaluate the distribution of your data, you can choose the most appropriate method for imputing missing values, ensuring the integrity and accuracy of your analyses. Remember, the best method can vary by variable depending on their specific statistics and the nature of their distribution. This method ensures that your data remains robust and reliable for any subsequent analysis or machine learning models, reducing the potential for bias that can arise from improperly handled missing values. This strategic approach to handling missing data is essential for maintaining the integrity of your data analysis projects. But, when it comes to imputing missing values in categorical variables like fuel type and met color, using the mode, the most frequently occurring category, is a practical and common approach. This method helps to maintain the integrity of the dataset's distribution for those specific features. So, the first step is understanding category frequencies. To find out which category is the most frequent, you can use the value_counts method. This will help you decide which category to use for filling in the missing values. This will display the frequency of each category within the fuel type variable, sorted in descending order. The category at the top is the most frequent. The output data clearly indicates that petrol is the predominant category with significantly more occurrences than diesel and CNG. When deciding on a method for imputing missing values in categorical data like this, the following considerations can be of most useful guide. Mode imputation. The mode in statistics is a measure of central tendency that identifies the most frequently occurring value in a dataset. It is particularly useful when dealing with categorical or nominal data, but it can also be applied to numerical data. This is the simplest and often most effective method for categorical data, especially when there is a clear majority category. In this case, petrol is the mode as it appears most frequently. Imputing missing fuel type values with petrol would be statistically justified given its high frequency, as it minimizes disruption to the existing distribution of data. Consistency and bias. Imputing with the mode, which is petrol, maintains the proportion and distribution of categories, reducing the potential bias that could be introduced if a less frequent category were used. Practical implications. Since petrol is the most common fuel type, replacing missing values with this category also aligns with likely real-world scenarios, where a randomly selected car is more probable to be petrol-fueled given the current data. Once we identify the most frequent category, you can use it to fill in the missing values in that column using the mode method. The .mode 0 accesses the first mode in case there are multiple modes. This value is then used with fill NA to replace all missing values in the fuel type column. Next, we are going to apply the same method to metColor categorical variable, so from the frequency of each category in metColor, we see that the value 1.0, which means the car has metColor, is reasonably high, so we will use the mode imputation in this case also. And after doing so, we can see that the frequency of 1.0 in metColor variable has increased. This approach effectively handles missing data for categorical variables by ensuring that the imputation does not significantly alter the distribution of the dataset. After completing the imputation for both numerical and categorical variables, it's good practice to verify that there are no remaining missing values. This final check ensures that all missing values have been addressed appropriately across all variables in your dataset, confirming that your data is now complete and ready for further analysis or modeling. Your approach to imputing missing values in both categorical and numerical variables is comprehensive and aligns well with best practices for data preprocessing. You've effectively used the isna function to handle missing data and demonstrated a practical method for applying these imputations across different data types. So, if we talk about summary of our strategy. For the categorical variable like fuel type and metColor, we have used the mode to determine the most frequently occurring category, or model value, and applied it to fill missing values. This approach maintains the distribution of categorical variables without introducing bias. For the numerical variable, we have calculated the mean or median values based on the distribution and presence of outliers, ensuring that the imputation reflects the central tendency accurately. For a more automated approach, you mentioned the use of lambda functions within the apply method to dynamically determine and apply mean or mode based on the data type of each column. This is an advanced method that enhances the efficiency of the imputation process, making it robust and scalable, especially useful when dealing with multiple columns of mixed types. After applying these imputations, it's crucial to verify the absence of any remaining missing values. This final check should confirm that all missing values across the data frame have been addressed. While the methods you've described are effective for many scenarios, it's always important to consider the specific context and requirements of your data analysis or modeling task. Sometimes, more sophisticated imputation techniques like k-nearest neighbors, KNN, multivariate imputation by chained equations, MICE, or regression imputation might be appropriate, especially in cases where missing data patterns are complex or not random. This approach offers a solid foundation for handling missing data, but always be open to adapting the strategy as needed to ensure the highest quality and most reliable analysis outcomes. Here's a brief recap of the key steps and methods discussed in this lecture are: detecting missing values. We began by using isnull, or isna, functions to systematically identify missing values in the dataset. This is crucial as it informs the scope of the data cleaning required. We highlighted how subsetting rows that contain missing values can help understand if missingness is isolated to specific columns or more widespread. This can reveal patterns that may indicate systemic issues in data collection or entry. We have seen random versus systematic missingness by determining whether missing data appeared randomly or systematically across the dataset. You were able to tailor your imputation strategy effectively. We performed mean or median imputation for numerical data. We chose between mean and median imputation based on the distribution of the data. Mean is used when the data is symmetrically distributed without outliers, while median is preferable in the presence of outliers to reduce bias. We implemented mode imputation for categorical data. The mode, most frequent category, was used to fill in missing values, which helps maintain the original distribution of the data. Lastly, continual verification post-imputation ensures that the interventions have correctly addressed the missing data without introducing new issues. Always consider the impact of these decisions on the overall quality and reliability of the dataset. We hope that you have found this course informative and interesting. Please hit the like button and subscribe to our channel and stay tuned for upcoming courses. Your support means a lot and motivates us to create more educational resources for you. In the next lecture we will start working on our capstone project of classification and regression. Stay tuned for the next lecture, where we'll continue our journey through Python's data science course. Thank you for watching and see you again in our next lecture.